Alright, so in this video we will be discussing esters. And so we'll begin with a method for producing esters called the Fischer esterification. And this method works by taking a carboxylic acid and reacting that with an alcohol in acidic conditions. And we produce the ester plus water. Now this is an equilibrium reaction. It can go forward and backwards, so it is reversible. But we can control the equilibrium by adding a large excess of the alcohol to drive the equilibrium towards the right. The mechanism for this reaction, I should clarify, this is a carboxylic acid, not the aldehyde. But anyway, the carboxylic acid plus the alcohol makes the ester plus water. And the mechanism for this reaction is to start again with the carboxylic acid. Because we're in acidic conditions, we can actually protonate this carbonyl oxygen on the carboxylic acid. So this is an example of the carboxylic acid acting as a base. Once we protonate that carboxylic acid, then a molecule of our alcohol can attack that carbonyl carbon and kick the electrons up to our carbonyl oxygen. So then there's a proton transfer step where we end up protonating one of these hydroxyls and deprotonating the alcohol. And so what this will do is we'll create this water leaving group, and the electrons from this other hydroxyl can come down, kick off that water, forming this protonated carbonyl again. So now we have a protonated ester. So we simply deprotonate. And that produces the ester. So we begin by protonating our carboxylic acid. The alcohol can then attack our carbonyl carbon, go through a proton transfer step so that we can kick off a water and form a protonated ester. Then we deprotonate that to form our final ester product. Now, there are two ways in which we can hydrolyze esters. The first way is simply a reverse of the Fischer esterification. So we take our ester and we react that with water in acidic conditions and with heat, and we will get back our carboxylic acid and our alcohol. And again, this mechanism is simply the reverse of the Fischer esterification, so if you take that mechanism and work backwards, you'll get the mechanism for this acid-catalyzed hydrolysis. The second method is a base-catalyzed hydrolysis. So in water with hydroxide, again with heat, and instead of getting the carboxylic acid, we'll get the carboxylate ion plus the alcohol. And this method is also called saponification. And a saponification reaction is what's used in making soap. That fats are a mixture of typically three esters. Oh, I think I've got that backwards. That looks better. And so when making soap, we start with a source of fat. We add sodium hydroxide, we heat it up, and we can break up these esters to form fatty acids or the fatty acid carboxylate ions. And that's what soap is made of. It's a salt of these fatty acids. And we'll go through the mechanism for the saponification reaction. And so again, we start with our ester. We have a hydroxide that attacks that carbonyl, kicks the electrons up to that oxygen. Then the electrons from that oxygen can come down and, wrong group, kick off the alcohol. So that forms the carboxylic acid. Then the alcohol will just pick up a proton from water. Forming protonated alcohol. And so the mechanism for the saponification is fairly simple. The hydroxide ion attacks that carbonyl, kicks the electrons up to this oxygen. Those electrons come back down and kick off the alcohol as an alkoxide ion, forming the carboxylic acid. The alkoxide ion then deprotonates the water to pick up a proton for itself, becoming the alcohol. Now, going through similar mechanisms to the hydrolysis reaction, we can have what's called transesterification. So in a transesterification reaction, We dissolve an ester in an alcohol. And I'll specify that that alcohol is different. We have a different R group. And this can be done in acidic or basic conditions. And we'll produce another ester, but with that different R group from the alcohol solvent. And so when we're working with esters, we need to be very careful about dissolving them in other types of alcohols, because we'll get this transesterification reaction that will change our ester. And so if we have like a methyl ester, if this R group here is methyl, then we should probably only dissolve our ester in methanol so that we avoid the transesterification reaction. If it were an ethyl ester, then we could dissolve the ester in ethanol to avoid the transesterification reaction. But obviously we can't do that with all of these R groups because not all of the those R groups will be available as an alcohol, or they won't all be liquids. They won't all make good solvents. But whenever possible, we should try to keep the ester dissolved in an alcohol that has the same R group as this ester, so that we avoid the transesterification reaction. So there are a few reactions we can do with esters that we can reduce esters that if we take our ester and we react that with, let's say, sodium borohydride, we'll get no reaction. The sodium borohydride is not a strong enough reducing agent. But if instead of sodium borohydride we use lithium aluminum hydride in diethyl ether, followed by an acidic aqueous workup, then we can get the alcohol. So we can reduce the ester all the way to the alcohol using lithium aluminum hydride. If we want to stop at the aldehyde, well, then that requires using a milder reducing agent such as dibol H or lithium aluminum tri-tert-butoxy hydride. So we can use either the dibol H or the lithium aluminum tri-tert-butoxy hydride, and we need one equivalent of either one. If we have an excess, we'll reduce the aldehyde to the alcohol. So we would defeat the purpose of using the dibol H or the lithium aluminum tri-tert-butoxy hydride. And so the reduction of esters can give us the alcohol or the aldehyde. And so we'll go over the mechanism by which we can reduce the ester. And we'll do that using aluminum hydride as our reducing agent. So one of these hydrides can attack that carbonyl and kick the electrons up to the oxygen. forming this tetrahedral intermediate. Those electrons from that oxygen can then come back down, and we can kick off this alcohol group as an alkoxide. And that will form the aldehyde. Now, once we get to the aldehyde, if we're using lithium aluminum hydride, a strong reducing agent, then another molecule of that aluminum hydride will come along, attack the carbonyl carbon of the aldehyde, and then during our acidic aqueous workup, we just need to protonate that oxygen forming our alcohol. So if we were using dimol H or lithium aluminum tritert butoxyhydride, we'd be able to stop at the aldehyde, and we wouldn't go through this second reduction to the alcohol. And so that's the mechanism for the reduction of esters. Next, we'll go over organometallic reagents. So in general, if we have an ester, and we react that with a Grignard reagent or an alkyl lithium, followed by ammonium in water, then we'll end up going through two reactions of the Grignard reagent to get the tertiary alcohol. And so we'll add two of these R groups to that carbonyl carbon and form the tertiary alcohol, because this will not stop at the ketone. Once we get the ketone, then we'll react that ketone with the second equivalent of Grignard reagent and form the tertiary alcohol. And so, as a little bit of practice, let's try to predict the outcome of this reaction, the ester and this 1,2-diol, under acidic conditions. We might think that this is like an aldehyde or a ketone reaction, that we would form the cyclic acetal, but we won't. This will not happen with an ester. Instead, what we'll get, because we're mixing an ester, an alcohol, under acidic conditions, we'll be doing the trans-esterification reaction and replacing this R group of the ester with our 1,2-diol. And so this will be the product of that reaction, rather than the acetal. And so we can't use our 1,2-diols as protecting groups for esters. So our next topic will be cyclic esters, which are also called lactones. And this is an intramolecular esterification with a molecule that has both a carboxylic acid and a hydroxyl group located at either the gamma or delta position. And so if we start with this molecule, and just to clarify what I mean by gamma or delta position, the carbons, whenever we have a carbonyl, we can label the carbons near that carbonyl with Greek letters. So the first carbon is the alpha carbon, then the beta carbon, then the gamma carbon, then the delta carbon, alpha, beta, gamma, delta. And so in this case, we have a hydroxyl group on the delta carbon relative to our carboxylic acid. And because we do this reaction under acidic conditions, then we'll begin by protonating the carboxylic acid end of this molecule. Then the hydroxyl group, its electrons can come around and attack that carbonyl, forming this cyclic molecule. We can deprotonate this oxygen here. I'm going to go ahead and show the protonation of one of these hydroxyl groups. Now we have an OH2 plus. So once we have this hydroxyl group protonated, it makes a good leaving group. Now we have water. The electrons from the other hydroxyl group can come down. We can kick off that water. Forming a protonated carbonyl. And we simply deprotonate forming our cyclic ester or our lactone. And an important example of a lactone is vitamin C. Now we have a 5-membered ring instead of a 6-membered ring, but we still have a cyclic ester. And so this is another example of a lactone. So that's how we can make esters and some of the things we can do with esters.